So we're going to begin this journey down geometry. We started geometry a couple of days ago, but we were kind of playing with shapes and sizes and strategies and things like that. But let's start at the core. We're going to do some rigorous geometry, but we're going to start with our imaginations because we pretty much have to. Geometry is a mathematical representation of physical ideas that we have. And it's not even clear how much we can relate these to the world that we live in, but we try the best that we can. But it starts with our imagination. And let's start with the idea of what is a point. Somebody describe a point. Anybody want to take a crack at it?
I'd say it's a dot.
Yeah, that's one of the easier ways to think about it. It's a dot. How big is that dot?
We are taught that it has no dimensions, neither length, breadth, nor height. So I don't think it should have any size.
There's nothing to measure yet, but it's the tiniest. We might try to think of it as a unit, but that doesn't even work because it takes infinitely many of them to make anything. But the point is that we have this object in geometry from which we make other objects. And we can make out of them, I don't know, we could make a line, for instance. We could put a whole bunch of them down, and it would take infinitely many of them to even make one portion of a line that we might call a line segment. There, that's a line segment. And that's something we can measure. We can measure its length. Okay, so we're dealing with these. Go ahead. So for the most part, what I'm going to do is I'm going to leave this first chapter that I've given you all. I'm going to leave this mostly to you for reading. There are not many problems to be worked here. It's mostly stuff that we need to think through. But here's a question. We'll think over a few questions. How many points define a line? Do you know what I mean when I say that?
Yeah, I think you're talking about how many points are required to make a line for it to actually count as a line, or not just
that's
two
like
dots.
It doesn't have a particular number, like infinity or a series of points make a line.
Well, here's what I mean. If I were to make one dot, how many lines pass through that one dot?
A lot of lines.
infinity.
Infinitely many. Even if we just stick to one plane, imagine my paper here as one plane. There are infinitely many lines that pass through. So one dot is not good enough. 1 point is not good enough to define a line. Okay. What about 2? How many lines pass through those 2 points?
Only one.
One.
Just one. So 2 points define a line. Okay. How many points define a plane? How many planes pass through those 2 points? If we think of ourselves in space.
I think infinitely many planes.
Yeah, and how would you describe those planes? Like, how would I draw them physically?
You can use your imagination.
Well, that's not quite what I mean. Look at this picture right here. What's true about all of those planes that go through those 2 points?
They are rotating around the line.
Yeah, they're rotated around that line. Good. And understanding that may help us solve some 3D geometry if we get to that point. Okay. And we can see why a table wobbles if one of its legs is too short. What is the line around which the plane that makes the table rotates?
I think the diagonal line from the I do not see. Yeah, there.
Right. Good. And that's a good mental exercise. So I don't know how much geometry any of you have studied, but in this first document, there's a little bit of discussion about how it is that we name objects. And I want to make sure that everybody's on the same page in terms of how it is we're going to describe a point or describe a line. And we usually use capital letters to name points, like right there. Call that point P. And then if we want to describe a line segment, we may use two letters, 2 points that are the end points, the beginning and the end of that line segment. And we might put a bar over the top of it. So now here's the thing. We could also call this line segment QP. But if we use one, we should probably use it consistently when we write mathematics. Once we start calling it PQ, it's just easiest for the reader to call it PQ. Now, array. What is array?
Array is a line segment that's extended on one side.
It's extended to one side infinitely, kind of like a line. We could call it half a line. That might work. But yeah, and we write it this way with an arrow, but that arrow must be extending in the correct direction. We start with the end point where it does not go on infinitely, and then we name in the direction of the second letter. And then here we talk about a line and we show the 2 arrows, meaning it extends in both directions. Okay. So far, so good. You can always refer back to this document to make sure, any symbols that you're not quite as familiar with, you can look back here for their definitions. This is the way we're going to mark equal lengths. To say that PU and ON are line segments with the same length. We can write it like this. Now notice that there is not a bar over UP and ON. What does that mean?
They are just lines and no longer line segments.
It's not that.
The midpoint of UMP.
I think it means that they are of the same length.
It means that they're the same length. When we don't put the bar over the top of them, it means that what we're talking about are quantities or measurements, lengths. So when we say UP equals ON, we don't mean that those are the same line segment. We mean that those are the same quantities. Their measured lengths are the same quantity. Well, measured or unmeasured, whether or not we know how long they are. And we see this often with midpoints. We have a midpoint that means by definition that the lengths on both sides are the same. and we say that two lines intersect. We might say they intersect in a plane as we've got them drawn here, but they could intersect in space. But when two lines intersect, they have exactly one point in common. How do we know that? How do we know that two intersecting lines have exactly one point in common? And this assumes that they aren't the same line.
Well,
This is
because
because
two lines could only cross each other at one point. They couldn't cross at any more or less. It could only be less if they are not crossing at all.
You've stated the conclusion. Well, you've stated one piece. If they didn't intersect, if they intersected in 0 points, then they wouldn't be intersecting, and that's true by definition. But how do we know 100% for sure? What if we had two lines that intersected in 2 points?
Then they would not be like straight lines. When we say line, there's just like it's moving in one direction only.
We could say, well, they're not really lines, but let's say they are. Let's say we have two lines that are lines, they're really lines, and they do have 2 points in common. That could happen. But what would be true about two lines that shared 2 points?
That one or more of them would not be a completely straight line.
No. You can have two straight lines that share.
The second line is on top of the first.
Top of each other?
How do you know? 100% for sure. How do you know?
Because a line by definition has to be straight, and for it to intersect with another straight line in more than 1 point, that line has to find a way to make it so that it either bends or is not. It either bends or is exactly on that line. That way all their points line up with each other.
I like the creativity. You're trying to describe how it is that a line would be forced to wiggle out of its shape or pattern or something like that. But how about this? We've already said that 2 points define a single line. So if two lines share those 2 points, what if we just say that demonstrates that they are the same line? And that's all we need to say. Once we know that.
Mr. Crawford, I thought you said you weren't the same line.
Say again?
I thought you said they weren't the same line.
Well, I said we had two lines. And how do we know that they're not? Well, how do we know that they can't intersect in 2 points? They can intersect in 2 points. They're simply the same line if they do. So there is only one such line. And that's the point. So
Okay. Thank you.
quickly moving on, just to make sure that we have all our definitions that are going to be important. Let's talk about polygons. We're going to talk about polygons a lot over the next 2.5 weeks. Polygons are figures. They're contained in a plane by line segments. No curved segments. So the first three up here are polygons, but the Pac-Man and the Ghost Monster are not. And of course we have edges and vertices. And I suspect you've heard these definitions before. And the one that we're going to study the most are triangles. Why would we focus so much of our attention on triangles?
Because there are many types of them, and each one of them have their own properties.
There are several types of them. Perhaps we could even say many.
They also make up a lot of polygons on their own. By combining certain triangles, you can form certain different shapes.
Okay. They make up a lot of polygons?
They make up all of them actually.
They make up all of them. What do you mean by that?
You can divide them so that they are made so that they break down into different triangles that form each shape.
Yeah, and sometimes we call this triangulation. We can triangulate any polygon. We can divide it up into triangles. So here are several things that we're going to find. One is it's already a challenge to study triangles. You know, we're going to spend hours, you know, working on different properties of triangles and learning how to relate triangles to each other and problem solve with properties of triangles. And once we do, we can apply all that to larger polygons, at least to a degree. But here's the thing, without triangles, it's going to turn out there's not much we can actually do on, you know, on a bigger scale, meaning with polygons with 4, 5, 6, 7, 8 sides. Almost everything becomes too complicated very quickly. So we have to rely on that simplicity of having just 3 sides and 3 vertices in order to make most of the important or interesting statements that we can make about polygons. And we'll start that today during this class. Circles. What's a circle? Somebody give me a good definition.
It's an enclosed shape.
It's a closed shape. Is that a circle?
It is an enclosed shape made of a curve and has equal proportions regarding its diameter, and its diagonals, and those it can be divided infinitely.
And I could probably take this right here and put it right here. The locus of points in a plane, some fixed distance from a single point. Now, what is this word right here, locus? Have you seen this before?
Yeah.
I've heard it somewhere, but I'm not really sure.
So in geometry, and this is a little bit frustrating at first when you're studying mathematics, in geometry, we often have words that mean the same thing outside of geometry, but geometry by tradition has its own language. So we have all these extra words that go along. And this word right here is the same as the word set outside of geometry. A set is a collection of objects. I could say A is the set of 1-digit prime numbers, for instance. There, that's a set. In geometry, we might have all the points that are 1 centimeter from a fixed point in a plane, and they make up a circle. So you'll get more comfortable with this language as we go. We won't be using it a ton early on. We'll be using it, you know, once in a while, but if you ever have any questions about this, you can, you know, tell me to stop. We'll think it through together. So these 3 at the top are circles. The next 3 are not. Actually, this one right here is based on circles. If we were to draw, this is an arc right here. Actually, I'll make the arc in green. It's the arc of the circle centered at that point right there. And if we were to start with an equilateral triangle and draw a 60-degree arc around its vertices, we could get this shape. Each arc is centered around a different vertex. So if a circle is the locus of points in a plane at a fixed distance from the center, what if we're in space? What if we're in 3 dimensions and we have a point P and we take all the points that are 2 centimeters from P? What do we get?
Isn't that a sphere?
Yes. So similarly round, but 3-dimensional. So one of the things that we're going to talk about, and this is going to be a little bit hard. I've never taught constructions by internet before. Actually, that's not true. I've done it just a little bit, but it's harder. It's harder because normally traditionally we use a compass and a straight edge. And what do I mean by a straight edge?
A ruler.
Yeah, well, you could say it's a ruler. Yeah, we don't care about the measurement part though.
Anything that provides you, that can help you make a straight line.
Exactly. That's all we care about, is that it's a tool that would allow us, like on a piece of paper, put that tool down and draw that straight line. So we're going to be able to draw straight lines given a position of a straight edge, and we're going to be able to draw circles. And those are going to be the rules. Straight lines with a straight edge or circles with a compass. So let's talk about how we would copy a segment. Let's say that we have this segment here and we're doing some problem solving and we want to be able to redraw it somewhere else. What could we do?
Mr. Crawford, is this without the help of a measuring tool?
That's correct. Without the help of a measuring tool, we just have straight edge and compass.
Well, we can just open the compass and make it so that the compass is touching A at one point and B at another point. And if we wanted, we can make B or A the center and draw a circle around it. Or we can just shift a point on the compass and then draw a line using the straight edge to repeat the circle. Sorry, the line segment.
Good. We could put, so maybe we'll say this is the needle tip of the compass down here. And then we have the drawing part where we can open it up to the width AB. And then we can put another tip down. We'll call that point C. And wherever it is that needle tip is, we can begin to trace a path of that width. And we could say, hey, that's a partial circle. The point is that any one of these points will have the same distance from C as A was to B. So we can use the compass to transfer length in that way. And we can transfer a length or a segment to a line. And if we needed to, we could have one of the endpoints already picked. And what would we do?
We do something similar to what we just did. We'd open the compass to the length of AB. Then we put the needle on E and just make a mark on either side of the line.
Yeah, we could put the needle at A and open the length width to B, then put the needle on E and draw the circle centered at E of that width and see where it intersects the circle. And there we have the segment transferred to a line, any line in the plane. Good. So here's the rule set. Given a point, you can draw a line through the point. Given 2 points, you can draw the line passing through both of them. 2 points define a line. Given a point, you can draw a circle centered at that point with your compass. Given a point O and a segment AB, you can draw the circle with center O and radius AB. You can open your compass to a width that fits 2 points. Given 2 figures, you can mark all their points of intersection. But you can never measure length. One thing that we will be able to do, though, is create observations that relate length. And we're going to be clever about that at times. We're going to skip a little bit, but I encourage everyone to work any problems that we skip through during this first chapter here. But let's talk about points of intersection and regions. Number 5, a circle and a line are in the plane. What are all possibilities for the number of intersection points between the circle and line? Or more briefly,
Is it 2?
So are you saying that a line and a circle must intersect in 2 points? I want all possibilities. Two is definitely one of them.
Two, one, and 0.
Is it possible if you could get 1 if the line is tangent to the circle?
Yeah, 0, 1, and 2 are all possible. Yeah, and just to be sure why, if you wanted, you could start with some point out here and imagine all the lines sort of radiating from that point, and take that line and turn it till it hits the circle. At the very first point where it hits the circle, then we have tangency, and then we can continue into the circle, piercing it and coming back out the other side. What is the maximum number of points of intersection between a circle and a triangle?
I think it's 6.
Yeah, I think it's 6.
Okay.
Because each line on a triangle, there are 3 lines on a triangle. Each line has a maximum of 2 intersections.
Good. I like that logic. We relate the triangle to the line because we already know the relationship between the line and the circle. And if we can maximize at 2 per line, then we're maximizing at 2 per line segment, since a line segment is a subset of a line. Okay, number 7. If I draw one line, I divide a region. I divide a plane into 2 regions. What about 2 lines?
4.
Wouldn't that be 4?
Now maybe I could draw it parallel to the first line and we have just 3 regions. But if I draw them intersecting, we seem to have 4. Okay. How about 3 lines?
6.
6, I can definitely get 6. Can we do better than 6?
Is 9 an option? Oh wait, sorry. Wait, it's
No,
okay.
8.
Can you draw me a picture in which 8 regions occur from 3 lines in a plane?
I can get 7.
Okay, Rishik gets 7. Can anybody get 8?
Should I draw it?
I got 7.
I'll draw 7 real quick. Won't take long.
Yeah.
It's just enough.
And
It's just enough that we kind of want to count them out this way, right? It's getting a little chaotic though. What if we keep going?
We could make the polygon corresponding to the amount of lines needed and like make the lines bigger, right? Like, oh wow.
With 4 lines, how many regions can we get maximum? None of the lines parallel.
Okay. 11.
So with 0 lines, we have 1 region. With 1 line, we get 2 regions. With 2 lines, we get at most 4. With 3, 7. And with 4, 11. How's this going to go?
It's going to increase by 6, 7, 8, 9, 10, 11, 12.
I think you just keep adding the number to the number before it.
Ah, we have a conjecture. What does that word mean, conjecture?
I'm not
I
so sure
guess
as to the definition,
we
but I
are
remember
supposed
that
to prove
it's
it.
like a hypothesis in math.
Okay. A conjecture is one of those things that we would like to be able to prove. We have a guess as to what's going on here. And the guess is when we add a number of lines, that the maximum of the number of regions increases by that same amount. So if that continues, we're going to have 16 regions with 5 lines and 22 regions with 6 lines. Okay, how do we know?
From our conjecture, we guess that you add the now 1 more than the previous number.
So here we have 11 regions by 4 lines. And if we were to start drawing another line, let's do this slowly and carefully and see what happens to the number of regions. I'm going to start drawing this line right here. I'm just going to draw a little bit right now because I want to focus on where we have new regions. Now we have this region up here at the top. And as this green line goes out toward infinity, that region is being chopped into 2 regions, isn't it?
Yes.
So it continues, it continues, it continues. And yeah, this other region is also being chopped into 2. And then the green line goes and it divides that region into 2 pieces. And that one. And that one. Is it going to hit any more regions? Sorry, that I didn't keep this particularly straight, but you get the idea. My geometric art is not of the highest talent level. And oops, until I look up here. It looks like we're adding 5, but how do we know for sure?
Because the green line divides each region 5 times.
We can see that, but how do, like, you know, what we want is a description such that no matter how many lines we had previously, we can say we're adding this many new regions.
I think because it divides through regions, and the number of regions it divides would, like, it would just add that number of regions to the amount that's already there.
Okay, good, good. We get a new region for every region it passes through.
Yes.
That's absolutely true. We get a new region for every region it passes through. How do we know how many regions it can pass through at most? What did I just draw there?
Points.
Any old points?
You drew the exact where it passes through to separate the regions.
The points I drew are between the regions that got cut in half. Not half, but got cut into 2 pieces. They're on the boundaries between those regions. They're on the other lines. How many other lines do we have?
Four.
Yeah, we had 4 other lines. So at most, we could cross 4 other boundaries between regions. So if we're crossing 4 other boundaries, 4 times we cross a boundary line. So at most, 1 more than that. It's kind of like fence post counting. At most, we have 1 more region than that. So the previous number of lines plus 1 or the new number of lines. And that is that's the best we can do. That is the greatest number of regions that we can add. And I'll tell you this is a problem that, we love to give this to students and let you all play with this problem. Sometimes it is given in terms of dividing up some piece of food, like a cake or a pizza. What is the greatest number of pieces that we can carve out given some number of cuts? Same question, just imagine the circle going off to infinity so that it's not really there anymore.
I realize that the number of regions you must add is the same as the number of lines.
So yeah, the number of regions that we add is the same as the number of lines. So now we can say if we gave our answer as a function, let's say f of n equals the maximum number of regions in a plane, chopped up by n lines. Can we provide a formula?
Yeah.
What would that formula be?
I think that would be the nth triangular number plus 1.
Very good. Wonderful. We start with one region, and then we cut one region up. With the next line, we cut 2 regions up. The next line, we cut 3 regions up. And with the last one, we add in regions. We cut through in regions. So that would be 1 plus the nth triangular number by definition. And if we wanted to, we could say, hey, that's n times n plus 1 over 2. And now we've got 1 plus n squared plus n over 2. And that would be n squared plus n plus 2 over 2. And that may be a little bit hard to look at. I do the same thing. I don't know who just offered this. I think of it the same way. I think of it as 1 plus the nth triangular number. Very good. Okay. Number 8. What is the maximum number of regions that can be formed by 2 circles intersecting in a plane?
Four.
How do you know?
Because 2 circles intersecting, the largest number of regions with just those 2 circles would be the intersection and then the 2 sides. But with the plane around it, that would be 3 plus 1, giving you 4. I don't know if that's the best way to explain it, but
it becomes tough to put this into words such that it's mathematical. It's far easier in geometry to guess an answer than it is to prove it. What about 3 circles? We'll come back to this. What about 3 circles?
I think it's 8.
Yeah, I got 8 as well.
Okay. What about 4? Actually, 4 is
12.
Maybe. 4 is a pretty tough problem, actually. But here's the thing. 1 circle gives us 2 regions. So we can say we start with like 2, 4, and 8. Or we could say we go 1, 2, 4, and 8. 0 circles, 1, 2, and 3. And one thing that's true about a circle is that it has an inside and it has an outside. This one boundary it's kind of like the lines in the previous problems. It can only divide up each region one time into an inside and an outside. At least as far as this problem goes. Maybe we could come up with some funky shaped regions and prove me wrong. But you know, for the purpose of this, each one is dividing into regions into 2 groups, one of which is inside the circle and one of which is outside. So the maximum number of regions that we can get seems to be multiplying by 2. That doesn't last forever. It gives us a maximum possible answer. And if we can draw it, and we can, for the first 3 circles, we can draw like Venn diagrams. We can chop things up into 2, 2 times 2, and 2 times 2 times 2 different regions. But it's going to get harder. And if you want to think about the further problems, I'll let your imaginations explore that another time. How can you cut a 3-dimensional cake into 8 pieces with just 3 straight cuts?
Well, you cut it down straight the middle, then you cut it at the side, and then after you cut it at the side, you then cut it along the diagonal.
I think that you'd have to cut it in each like in each direction. So you cut it lengthwise, you cut it widthwise, and you cut it depthwise. You know.
What if you cut it?
Go ahead, David.
Okay, I was thinking that you'd cut it without cutting all the way, but now that I think about it, doesn't seem like that would work.
To get 8 pieces,
Try making it.
Sorry? To get 8 pieces, we could have 2 layers, a layer on top with 4 pieces and a layer on the bottom with 4 pieces. So first you create the 4 pieces, and then you separate the 2 layers to get 8.
So I'm going to say this. My imagination just isn't very good. So I need to draw this. I want to figure out what's being said here. I'm going to draw a big cubical cake, just to be simple about it. And so this means I need to practice how it is that I draw a cube. You know, it's hard to draw 3D objects in 2 dimensions. You know what though? I can draw a square easily enough. I draw a square. I can take a 1-dimensional segment, move it over, and then connect the corresponding vertices. Well, maybe I can do that again with to make a cube. To turn this square into a cube. Actually, I'll start over. I'll make a new square. Start with 1 vertex. Copy that vertex some distance away and connect. And then I'll copy this entire line segment, that same fixed distance away, in another direction. And then I will connect the corresponding vertices. But I'm going to do all of this over again, and I'm going to imagine that I'm kind of taking an angled movement through the screen to pick a new position for the new square. And then I'll finish drawing that square. And then I will connect the corresponding vertices. And now I will consider this cake that several of you are telling me how to chop up here. I'll consider chopping it in each one of these dimensions. I'm cutting through 4 edges. How many edges does a cube have?
12.
Yeah, we've got 12 edges. 4 for a square, then we copy 4, and then we create 4 new ones for the corresponding vertices. Okay. So we cut through 4 of those at a time. And there, we've done it. And it may be hard to see. I don't know how good my drawing is here. It may be hard to see, but what I can see is that as I made each cut, I was creating one side. I was taking a region, and for every region, we had one side, and then we had the other side on the other side of the plane, and every cut was traveling through all of the previous regions. So by traveling through all of the previous regions, I know I am cutting each of them into 2 pieces. And each piece right now corresponds to a vertex, and that makes it a little bit easier to count. Okay. Moving right along. I'm going to leave this one for you all to enjoy, number 10. Consider that one homework. Okay. Let's talk about adding and subtracting lengths in construction. Okay, let's say that I want to be able to draw one straight line segment whose length is AB plus CD, and I want to be able to draw one whose length is AB minus CD. What do I do?
You could start by drawing a straight line, just extending it. Then with your compass, you copy the length of AB
Actually,
into that line.
before you say everything all at once, I just want to mention, I'm going to give this line a name, and we haven't talked about how we name lines. With points, we usually use capital letters, and for some reason, by tradition, we use cursive letters, usually, to name lines. That's if we don't name them according to, I could talk about line AB and name them according to the points, but we could just give them a simple name like L, and that's a little bit more traditional than calling the line, I don't know, David. So we'll call this line L instead of David. So David, continue.
So then you could use our compass to copy the length of AB onto that line, then add CD, like by standing on one side of the copied AB on the line and making a different mark on that line. I don't know if you get me.
Okay, so I was a little slow getting set up here. Let's say that we've copied AB to EF on the line. Now, what do we do?
Then we, with our compass, get the length of CD, then put the needle on either side of EF, then mark on the other side of the line to touch the other line, to touch the longer line.
Okay, we'll open our compass to that length. And then with that compass, we can draw this circle around F, open to that compass length. And if we call this point over here G, and we call this point of intersection with the line in the circle H. So these are the points of intersection between the circle and the line, G and H. And now this whole length, EG, big one, is equal to the length of AB plus the length of CD. Similarly, EH, which is EF minus HF, has length AB minus CD. Okay. So I'm going to go ahead and say, let's move to our second piece of this lesson. We are going to talk about angles. And we may not go through every part of this document, but I encourage you to make sure that there's nothing here that you don't give some practice. But, you know, what is it that we're talking about when we talk about an angle?
I think when we mention angles, we are talking about a measurement that shows us the degree, showed us how far away sort of another line that intersects with another line is from it.
Yeah, how far away? Yeah, I like those words and I don't like them at the same time. Yeah, it's actually tough sometimes. And this is the problem with geometry, is that we're building in our imagination to relate real world stuff to something that that is only in our imagination. And we say distance. Well, normally we have one concept of distance, but you know, we're opening up. You know, we have two rays or two intersecting lines, but I'll say two rays. You know, maybe we start with one, but we just say, hey, let's like open up a compass, you know, or it's kind of like thinking of that fulcrum where we're bending something, and we kind of create more and more space as we go. And you might think of that as distance. How do we describe that space? How do we measure that space? And we measure it relative to a whole circle. And we say that a whole circle has 360 degrees. And we open up to some number of degrees, maybe 39 degrees here. I'm just going to guess. But where does that come from? Why do we have 360 degrees in a circle? $360 going all the way around. What does that remind you of? 360, 360, 360.
I almost said the number of days to make a year, but I'm not sure.
That's a pretty
Because that's 265.
I think that's fully reasonable. I actually don't know the history for sure. I don't know why 360 was chosen originally, but
Yeah, because sometimes I ask myself, why didn't they choose any other number? But
I think that it's a combination of two things. I think it's a combination of 365 days in a year. 360 is close to that. What else is true about 360?
I think because it's divisible by a lot of numbers.
Yeah. I think it's both the number of days and good divisibility. How many divisors does 360 have? How many positive divisors? I don't know this off the top of my head. Let's compute it. How many positive divisors does this have?
Is it 24?
Yeah, 24 positive divisors. And that's nice.
Wow.
We can chop up the angles around a circle into 3 or 4 or 6 or 8 or 12 congruent pieces.
Or even 9.
Or even 9. That's right. And that's going to allow us a lot of advantages in problem solving, where while we're doing the angle math, it comes out with nice integer numbers. Okay. So here, somebody has drawn for us two parallel lines. And then they've drawn crisscrossing lines. Now, what is this about right here? So do you know what a postulate is? Anybody?
We did them once in class, but I don't think I remember.
A little while ago, I said we just have to tolerate the fact that geometry has its own language. This is one of those times. Just like locus in geometry is the same as set in other mathematics, postulate in geometry is the same as axiom. A postulate is an assumption. It's something that we're allowed to take for granted, and we come up with a few assumptions on which our study of geometry rests. And this will be a little more clear as we go. We have to in order to claim that we have proved anything about geometry as we go. And I'm going to go ahead and talk about one of those postulates as we talk about angles and parallel lines. So I'm going to draw a couple of parallel lines, and forgive me, like I said earlier, I'm not the best geometric artist, so sometimes I kind of do okay, but this was okay right here. These look like parallel lines, don't they? Some of you can probably do better. Most of you. Okay, I'm going to draw these two other lines right here. And these two new lines that I've drawn, we call these transversals. Actually, you know what? Let's stick to one for the time being. I'm going to draw it like this. And we call this line that's, cutting these two parallel lines, we give it a name, transversal. It will be clear why we give it a name. This is special. This drawing is special. we base one of our postulates on it. If we were to, get some sort of a measuring device, what device do you use to measure angles on a piece of paper?
A compass.
Protractor.
Yeah, protractor. Protractor is one of those. It's a semicircle, and it's got tick marks that go all the way around it that chop it up into 180 units, and we can just see how many units we go across as we get to some point as we're measuring around. If we were to get one of those devices and put it down on this drawing that I've drawn here, here's what we're going to find. We're going to find that this angle right here is the same as this angle right here, which is the same as this angle right here, which is the same as that angle right there. All four of those angles are the same. Furthermore, this angle right here is the same as this one right here. This one right here is the same as this one right here.
So they are vertically opposite.
Yeah, we call those vertical angles. And any of this terminology that you're not familiar with, it's going to be, in the chapters that I posted. Get used to any of the geometric language that you haven't already. And I've marked these angles as equal in these two different ways. But here's the thing. In geometry, we don't prove this. We assume that it's true. Right? The fact that those angles are equal in the way that I said they are is an assumption. This is a postulate. This is one of those things that we're allowed to assume, and it's going to help us prove other things. In fact, it's going to help us prove a lot of other things. But somebody give me an intuitive explanation. How do we know these angles are the same? Can you describe something in the physical world that's like this?
Well, we can tell that these angles are the same. I don't exactly have an example off the top of my head, but if we were to make this line straight, we would realize that it'd be 90, 90, 90 all around, and they'd be equal. And if we were to take the first two on top of one of the parallel lines, the first two angles, we would see that the same amount at which we increase the angle on the left side of the line, the angle below, on top of the parallel line below, will increase by the same amount. And it will be the same reason for the opposite side of the line crossing the parallel lines. So it would decrease by the same amount.
It seems intuitive that it would. It seems intuitive. I like to imagine watching a rocket ship blast off from Earth. I've never seen that in real life. I've seen it on TV, but I imagine a rocket ship blasting off, and as it approaches the cloud layer, the clouds are in blue, and maybe it's a day where there are two layers of clouds, but the rocket ship, maybe it's already it's taken off and it's turned, and now it's going at one direction without curving anymore. And it goes through one of the cloud layers, and then it goes through the other. But these cloud layers, if they're just flat layers of clouds that are out in the sky, the rocket ship doesn't see either of these clouds differently. It sees them the same way each time it passes through one and then passes through the other. And so it's an identical situation. So that's the way I view it. Anyhow, this is a postulate. And let's see what it is that we can do with this postulate. Well, oh, by the way, I'm going to mention, I'm not going to stop and go through all this language. This is just something you'll have to get, used to in the reading. But we have names for some of these angles, like this one right here and this one right here. We call alternate interior angles. And we say alternate interior angles are equal. Okay. And then we have same side. So if we didn't choose them on the opposite sides of the transversal, we could have chosen them on the same side as the transversal. So alternate interior angles are equal. same side interior angles. Later on, we're gonna describe what supplementary means, but they are supplementary. And then there's interior angles, and there are also exterior angles. And the difference is whether or not they are between the two parallel lines, interior to them, or exterior to the parallel lines. But the important thing is that you can pick out which ones are equal and then put the words to describing the positions. Sorry, I'll let you do all this reading, but I'm moving forward to the next lesson that I want to talk about.
And will we treat polynomials in this
How
class?
do you know? Don't say things that I don't know.
No, our brief conversation about polynomials, I think, is all we're going to do.
I already knew what you were going to say.
Sorry, with polyominoes. Okay. Next thing we're going to sort of write our first geometric proof, get our first theorem. And somebody mentioned earlier vertical angles. And if we have this line right here and this line right here, we're going to talk about what it is that we can demonstrate. I'm going to name some points. The point of intersection I'm going to name P. Then I'm going to go around, I'll call this A, B, C, and D. And let's talk about what it is that we know. Well, there are some very simple observations that we can make about angles. For instance, I can say angle A, P, C is 180 degrees. We call that a straight angle. And I know that doesn't seem very interesting, right? I mean, there we go. It's a straight angle. But it's all these very basic, simple things that we look to in order to make more interesting statements. Can we see angles that make up APC? Might be more interesting to talk about.
Angle APB and BPC.
Right. Those two smaller angles, that one plus that one, make up that whole straight angle. So they add up to 180 degrees. And what do we call two angles that add up to 180 degrees?
Supplementary.
Yeah, two angles that add up to 180 are supplementary. If they add up to 90, they're complementary. But for our beginnings, our base of geometry, we care more about supplementary angles. So they add up to 180. Can you pick two other angles here that add up to 180?
Angle APD and DPC, they also add up to 180.
That's true. What's one more pair?
Angle APB and angle DPA.
Okay. And notice I did something right here. This angle and this angle are the same. It doesn't matter which one of these letters I write first and which one I write last, so long as the middle one is the one around which we are rotating. Okay, now I want to point something out. This first equation and third equation have a same angle. Huh. In fact, the second and third have a same angle. What could we do with those two equations as a way to get a look at the relationship between those angles?
Well, we can say that since dpa is mentioned in two equations, we can say that what it sums to 180 is the dpc equals apb.
Now, there are several ways we could say this, but I'm just going to say by transitivity, the two left-hand sides both equal 180 degrees, and therefore they're equal to each other. So angle APD plus angle DPC equals angle APD. I'm just rewriting that. APD plus angle APB. And now we can subtract that angle out of both sides. And this is algebra, right? Even though we're talking about geometric stuff, our same notions of algebra apply when we're using equations. So let's see, DPC and APB must be the same angle. This angle right here and this angle right here necessarily have the same measurement. And here's what I want to point out about this. This could have been any pair of angles. There's nothing about this that doesn't generalize. If we have two lines that intersect in a plane, and we can say that each of them is supplementary to that other angle in between those lines. Supplementary angles, supplementary angles. And that gives us two equations where we can subtract off that gray angle in between them. Therefore, vertical angles are always equal. Any questions about this? Okay. So now let's talk about another postulate in geometry. And this is going to be the most important one ever. And it seems, it's a little bit weird that we come to the most important one ever on day one. No, it's not really. It's foundational. But this one also involves parallel lines. And we, in fact, give it the name, the parallel postulate. And when I say this is the most important one, I am completely serious. If you ever forget what it is that we're doing along the way, like how it is we're making these connections in geometry, there's a very good chance that you can go back to this and rebuild everything that we do in geometry, or a lot, not everything, but plenty. Here's what the parallel postulate says. It says that if we have a line in a plane and a point in that plane not on that line, then there is exactly one line in the plane through that point that is parallel to the original line. Exactly one. Well, what all does that mean? It it means that the new line, which is parallel, it exists. Also, that line is unique. It exists, which means that there is at least one. It is unique, which means there is at most one. So there's exactly one. Ta-da! So you may be thinking, well, what's so special about this? Well, let's see. I'm going to draw a triangle, any old triangle. Oh. I know that you will all help me out by pretending that my lines are straight. So let's examine this in terms of the parallel postulate. We don't have many tools to work with in geometry. I mean, we're starting with almost nothing here. We have a few words like points, and otherwise we're like, hey, this is all in our imaginations. But we have this tool now that we call the parallel postulate. It involves a line, first and foremost. So somebody identify an interesting line in this diagram.
Line B.
Well, there would be a parallel line to BC that passes through A.
Oh, slow down. If you know this, if you have the idea already, don't tell me the idea. Just tell me an interesting line in this diagram.
Line BC.
BC, right. Here is line BC, right? I want to talk through this whole thing because I want to impress upon you the idea behind it, because if all the relationships are cemented in your mind, all of your hard geometry is going to seem a lot easier. Here's a line. It's an interesting line in this diagram. So what is an interesting point in this diagram not on that line?
A.
That is definitely the most interesting point in this diagram, not on that line. And now, what does the parallel postulate tell us? Salorm.
That there's a parallel line to BC that passes through A.
Right. A is a point in the plane not on BC. The parallel postulate says that there is exactly one and only one line through A parallel to BC. Okay, so now we have parallel lines. What can we make of these parallel lines? How does that help us?
You can find angles by extending the lines.
Right. Our other postulate told us that when we have a transversal, AB would be such a transversal. AC is also a transversal, but let's focus on AB for the moment. We have equal angles. We know that this angle and that angle and that angle and that angle are all the same. Okay, that's good. You know what? If something works, let's continue doing that thing. Let's try that again. We look at the other transversal. We kind of extend it in both directions, the line in both directions if we need to. We can look at that other transversal and say, oh, hey, look, we have vertical angles right here. And then on the other side, we have those corresponding angles from the parallel lines. Well, that's great. We have all kinds of information. We created information out of thin air, didn't we? That's what's important about the parallel postulate is we have almost nothing, but boom, we create information out of thin air. And then finally, this is the third angle of the triangle, right? We have, the angle at B is one of the blue angles. The angle at C is one of the green angles. The angle at A, well, that's just another angle. And where do we see those three angles together in a way where we can make an interesting statement about them?
Well, all of them can be found within the triangle. Can I go on, or is that?
That's one of the interesting things that we can say. Those three angles are the three interior angles of triangle ABC. What else is true about those three angles?
All of those angles add up to 180.
There they are together on one side of a straight line. Therefore, they add up to 180 degrees. Therefore, the angles of a triangle must add up to 180 degrees. And we prove that using these two postulates that involve parallel lines. Okay, let's do a little bit of problem solving. I'm going to pick problems that are not in your handout. Let's say that we have two parallel lines. We'll call them M and N. And then we have a transversal with W, Z, X, and Y. And this is 113 degrees right here. And then A, B, and C. And I want you to find the values of all those different variables. So I want 7 different people to answer. So give me the value of A.
A will be 180 minus 113.
It will be 67 degrees.
Okay. What about B?
It's the same 67 because they are vertically opposite.
Okay. So somebody who hasn't answered yet, what is the measurement of angle C?
113 degrees.
And Archie, tell me what is X?
That would be the same as C. So 113 too.
So here's X. And we know that X and Z are the same. What other angles are the same as X?
Oh, sorry, I mean 67. Sorry, I got confused. I thought, yeah, sorry.
That's all right. Good, good. And now Y is equal to
113.
113. Okay, good. Just a little basic practice. And we'll do one that's a little bit harder here. So we'll say that those two lines are parallel, and then we're going to draw 2 more parallel lines. And then we're going to draw another line that goes through B and D. Almost. And let's say that this angle is X, and this angle is Y. This angle over here is 3X minus 15 degrees. And this one up here is 3Y plus 15 degrees. And we want to find the values of X and Y. What can we do here?
Okay, we know the value for A is 3y plus 15. So the Other angle on the same straight line will be 180 minus 3y plus 15.
Okay, yeah, we can chase angles.
Oh, we can also do this.
Oh,
Three.
hold on. Give me one moment, Manvendra. I just want to introduce that concept right here. We're using the few things that we have learned so far about angles to chase around the diagram other values. And one of them was we could subtract 3y plus 15 from 180 and say this is 165 minus 3y. And now those two angles next to each other add up to 180. So that's one of the things that we can do. Manvendra, give us another thought.
I thought of if you could add 3y plus 15 degrees and 3x minus 15 degrees and equal it to 180. And then we can solve it as a double variable equation.
Okay, so you claim that 3x minus 15
plus
3y plus 15 degrees, you claim that's equal to 180 degrees. Is
Yes.
that according to a postulate or a theorem?
Yeah. It's, how do I say it? It's,
What postulate or theorem tells us that?
I think it's his conjecture.
it's corresponding, I think. Is it corresponding angles?
So
No, both of them are on a straight line, and angles on a straight line add up to 180.
They're not on the same line, actually.
Yeah, but they're on the same positioning, which
Yeah,
can
the same
show that
position
they're
on the
same
line. So I think these are corresponding angles.
So here's the thing. In order to apply the postulate that allows us to name corresponding angles, we have to identify the parallel lines and the transversal. For instance, if we identify this line, and then we identify this transversal, well, look, nothing around A is part of that. Right? We can talk about this, this angle right here around C, but we can't directly compare it to anything at A. However, what can we say?
And we can find the vertically opposite angles of A and the opposite one, which will be corresponding to the angle on top of D and Y and the angle we don't know.
If those four angles are equal, now if we want, we can say, we can look at this line and the transversal through A and B. Then we can say this angle right here corresponds to that angle right there. Or you could say that it is supplementary to that angle right there. So here's my point, is we make two applications right? This postulate, this postulate up here, it's only got one pair of parallel lines and one transversal. We have to go one step at a time to be sure that we can prove our claims, right? Our first step was to use those two parallel lines and that transversal and transmit the information about this angle up to here. But then we use a different pair of parallel lines and a different transversal, and that allows us to make a second relationship. Then we have our equation. So we have one equation involving two variables. We need another one.
3x plus 3y equals 180.
Oh, that's true. That's a simplification of our equation. We need another relationship. One relationship is not going to be enough. Let's go ahead and find that other relationship.
Well, if 3x minus 15 is equivalent to 165 minus 3y, then based on that, we should be able to divide 165 by 3 to get x, and then 15 by 3 to get y.
We're still going to need more information. I understand. We can work with that equation, but that's not what I'm asking. I'm asking for another relationship, another equation that we can work with, because one equation will not be enough. Let's remember.
Okay,
Plus
then
y equals x minus
3y plus 15 is corresponding to the angle on top of D. So we can subtract 180 for me to get the total angle for y.
Okay, we can do that. We can do something more direct, right? We used the upper right-hand corner. We kind of focused around this corner to transmit information through. While we were doing that, I noticed, hey, look, here's angle y, and here is angle y. Then here is angle x, and vertical angles are equal, so there is angle x. So now what do we know?
by set
X
x plus y equals 3y minus 15. I think it's x.
There we go. And now we have two equations and two variables, and we can solve. So everybody go ahead and solve this system and tell me what you get.
Miguel, y is equal to 2x minus 15. We get 25 and 35 as the values of x and y. Okay, let's take a look at one more. So these are parallel lines. And I'll use little arrows like this to denote parallel lines when we have them.
Okay, I want you to solve for x. I'm going to step away for just a moment while it is that you all work on this one. I'll be back in just a moment. All right, has anyone cracked this one open yet?
Yes.
I'm here.
Okay, Adriel, can you get us started?
Well, so y plus 3x is equal to 140 degrees.
Okay, so yeah, we can transfer that 140-degree angle. Well, we can't say that directly though, right? This is like the last problem. We don't have a postulate that tells us directly that we can just go to, you know, from here to here. What do we have to do?
We have to apply the rule for vertical angles. So we find that W equals 140, and since W equals 140, Z equals 140, and the opposite to Z also equals 140.
Okay, so we can say corresponding angles are equal and go from that angle at W to that angle at Z that I just marked. And if we want, we can mark all these angles around Z. Right, in order to make these statements, we have to have two parallel lines and a transversal. We use this line and this line, but the angles around W and Y do not share a pair of parallel lines, so we can't just jump there. We have to justify what we're doing. Now we can transmit some more angles. We do have an angle of, now we can use this line and this line is parallel. And we can say, yeah, this right here does equal 140 degrees. Okay. So what? That's 140 degrees. Now what?
That means the side beside it will be 40. So if that side is 40, then beside X would be 40. Yeah, and the next place would be 50. Since that whole place is 90.
We have a right angle, and
Yeah.
since one of the pieces was 40, the other one's 50. Okay.
So if X plus 50 is 3X, that means X is half of 50. So X is 25.
Those two are vertical angles. And so now we have an equation, two ways to express the same quantity.
Yeah, so X is equal to 25.
X equals 25. Good. Okay, one more here involving parallel lines. Let's say that we've got a pair of parallel lines, and then we begin drawing from one, and then we cut and move 90 degrees from the angle that we started moving. If this right here is 130 degrees, what is that down there?
It's 50 degrees.
How do you know?
Because the angle opposite to X will be also 130 because it will be corresponding. So 180 minus 130 will give you 50.
Corresponding, we don't even have a transversal.
Well, Mr. Crawford, I was thinking that since the opposite of 130 is 50, and if we were to put a parallel line in between the 90, we'd realize that would also form another 50-degree angle.
Okay.
And from
this is the right idea, is that we identify an interesting point in our diagram, and by the parallel postulate, there is exactly one line through that point parallel to either of our original two lines. And so it is parallel to both of them. Now we have transversals. Now this is a transversal, and that is a transversal. And through those transversals, we can transmit angle information. So we have this angle is equal to this one. Now somebody else. What else can we mark in this diagram now? Shreya?
Could I try?
Go ahead.
Since that place is 50 and that's a right angle, the other place would be 40. So since it's alternate to X, X is equal to 40.
Okay, yeah, we have alternate interior angles, and alternate interior angles are equal. Therefore, we have 40 degrees. Good. And this problem it's otherwise hard if we don't identify this line between the other two that's parallel to them. And just remember, like if you're stuck, if you're not sure what to do, if you think you might need free information, it's not entirely free. You have to work to get it, to see where it comes from. But you get numerical information out of angles. Ask yourself, is there an interesting point in this diagram through which I can draw a line parallel to something else? Okay, one more theorem for the day before we go. Okay. What is the question mark angle?
It's x plus y.
How do you know?
Well, we
Because the
recently
sum of two
proved
interior angles is equal to the exterior angle.
Well, that's a claim, but I want us to prove any claim that we make.
Well, because x plus y plus the other interior angle gives you 180. So angle C, so the other side would be angle C, sorry, 180 minus angle C, which is the same as x plus y.
Yeah, so the exterior angle, any exterior angle at an angle of a triangle is equal to the sum of the other two interior angles. And I'll go ahead and tell you this about this theorem. This is one of those where it's so quick and simple to get there that it feels like we don't even really need it. But observationally, it becomes helpful as you get into some challenging geometry. And now let's present one more problem for the day. Let's say that we've got a segment right here. Try to draw that horizontally. And let's say that we have a line going straight up and a line going straight down, but they are parallel to one another. And we have a right angle right here. I'll call this point A, and this one B right here. And then we're going to draw from A to a point E. Now we've got a triangle, and then B to C to D. And we're going to say this angle at D is 3x, and this angle up here at C is x, and this other angle at C is 3x, and then 50 degrees right here. And I want you to find x.
We can start by drawing a straight line across the C so that we can get a transversal by extending the line.
Maybe. I don't think we need any new lines in this diagram.
Well, maybe let's start by looking at the bigger picture and realizing that the triangle ABE has a 90-degree angle at the corner.
Okay, so we have parallel lines, and AB is a transversal between those parallel lines. And yeah, we have alternate interior angles right here. So good, we have a right angle there.
And now that we know that there's an angle there, we also know that the sum of the angles in the triangle is 180. 90 plus 50 is 140. 140 from 80 means the angle at A is 40 degrees.
Okay, good. We found a little new information.
Okay, if you take
Okay.
Now, Norley, what were you going to say?
I was saying if you take triangle CBE, you can say that 3x plus 50 degree plus the angle EBA will give you 180.
EBA, that's the right angle?
Yeah.
But you were in triangle CEB?
So angle EBC will give you 180 plus it will give you 180.
Okay, EBC, not EBA. That's true. Those three angles add up to 180, and we might
Okay.
something like this angle here is 130 minus 3x, but we don't need to go that far. We have enough information at this point that we're going to be able to jump to the answer very directly. And I'll give a hint.
Well, we could use the theorem that he just taught us because the angle CDA is the result of the addition of angle BCD and then angle CBD. So we could then find out that angle CBD is equal to 3x minus x, which is 2x.
More work than we need. If I understood you correctly, we have two interior angles of this gray triangle. What else do we have?
The exterior angle X, which is equal to the sum of 40 plus 3x.
It's not X, not Norley. What is the exterior angle at C relative to that gray triangle?
Well, we know that the sum of the two angles is equal to, can be subtracted from 180 to give you the angle at C. So we can say that 40 plus 3x equals 3x plus x. So
Which is 4x.
3x plus x. That's it right there. That's the exterior angle. And the exterior angle theorem tells us that the exterior angle is equal to the sum of the other two interior angles. And of course, we can just subtract 3x out, and we have our answer. So, and we could have, we could have danced around. We could have said, hey, look, 3x plus x is 4x. So this angle here is 180 minus 4x. And then the sum of these three angles makes 180 degrees. But this is part of the point of the exterior angle theorem, is that you just see it more directly, especially as you get used to it. So there are some practice problems. We went through two of the three files that I dropped into the Piazza page, and we went through two of those today pretty solidly. There are some extra problems in there. There are probably some extra problems in your Art of Problem Solving Volume 1 that relate to these lessons, and give those some practice. And tomorrow you'll have a test, and it'll have a little bit of what we covered today and a little bit of what we covered Monday. And I hope you all enjoyed it. I'll see you on Friday.
Bye.
Thank you, Mr. Crawford. Bye.
Welcome.
Thanks. Bye.
Okay, thank you. Bye.